In this video, I want to introduce you to something called complex numbers. Okay, so up to now, you may have seen in your previous mathematical adventures, you may have came upon a situation where somehow by accident or who knows how, you ended up with, you were staring at the square root, let's say, of a negative number. Okay, and then you might have recoiled in horror and said, whoa, that doesn't make any sense. You can't have the square root of a negative number. And if you said that, you would be correct. You can't have a regular number, what we call a real number. You can't have a real number that's equal to the square root of a negative number. Okay, but math, you can, in a sense, you could think of it as a game. Remember how maybe you've made up card games in the past? Somebody at some point said, you know what? What if we pretended? What if we made up a new type of number and we said that it was equal to the square root of a negative number? All right, and that's exactly what happened. And it turns out that it was more than just a game. It was actually very useful for math, for science and engineering. Okay. If you know what an electrical engineer is, people that work on circuits like that go into your house to power your house, the mathematics of electrical engineering uses, in some parts, it uses these new types of numbers. Okay? And if you've ever worked or seen, if you've ever seen 3D graphics, right, like certain games like Minecraft, that you could, there's 3D worlds, okay? The software that people write that allows you to simulate moving through a 3D environment, a lot of the mathematics of that also uses this new type of number, okay? So this isn't, even though I'm talking about it like it's fun and games, it actually turned out to be useful, okay? So how are we going to handle talking about the square root of -4? Okay, so the first thing we're going to do is we remember from when we learned about square roots, when we learned about radicals, we know that the square root of a product is the product of the square roots. So let me write this as the square root of 4 times -1 times it. So in other words, what I can, and I know how to do the square root of 4, that's 2. Okay? We can always isolate the weirdness with a -1. Okay, if I had like the square root of -16, I know that -16 is -16, or plus 16 times -1. So the square root of 16 times the square root of -1, or 4 times the square root of -1. Square root of -25, I can work that out, and that one is 25 times -1, square root of 25 times the square root of -1, so 5. So notice that for any one of these weird square roots, I can always boil everything down into something that makes sense times the square root of -1, which up to now did not make sense. Okay. So this comes up so much that in order to avoid having to write out the square root of -1 all the time, we actually have a new symbol. Okay, because it seems like this isn't a real number. Well, it isn't what we call a mathematical. It doesn't belong to the set of real numbers. So half seriously, somebody at some point said that these were imaginary numbers. Okay. For that reason, we're going to call the square root of -1 I. Lowercase I. See that? So the first result, I can call that 2I. The second result, I can call that 4I. The last result, I can call that 5I. Now, every time you see the I, know that it's just an abbreviation for the square root of -1. All right. Now we can continue playing this game and we can define multiplication, we can define addition, subtraction, multiplication, and eventually addition for these new types of imaginary numbers. Okay? And it's the rules of this new type of arithmetic are probably exactly what you would think of if you were making up the simplest rules that made sense. Okay? Let's try to see, what do you think it means to say 4i plus 3i? How should we define that, or how should we understand that? Well, whenever you get confused, write out what it's an abbreviation for. So this is 4 times square root of minus 1, 3 times square root of minus 1. We all know that if you have 4 apples plus 3 apples, that's equal to 7 apples. Okay? So 7i. So apparently you can treat I just like any other quantity. Okay? Now what I just showed you is a definition that would make sense. Or that would be the natural way to define it. And indeed, that's how we define the addition of imaginary numbers. Okay? We also define, likewise, subtraction. So 5i minus 2i is 5 minus 2, that's 3, so 3i. Okay? What about multiplication? Okay? We will leave that one to later, but for right now I just want you to start thinking about it. Okay? And let me do one multiplication problem. Let's say I just wanted to do exponents on the I. So like I squared. Square root of minus 1 times square root of minus 1. Well, that is using the old rules of arithmetic. We know that the square root, this is basically the same square root times itself. We know that that's equal to whatever's underneath the square root. So in this case, minus 1. So apparently I squared is equal to minus 1. Okay? I cubed is I squared times I. You can just write out all the i's. I squared, we already figured out that that's minus 1 multiplied by the leftover I, so we get minus I. Okay? Now watch how simple the next one is. I to the 4. That's equal to I squared times I squared, but I squared is equal to minus 1. So that's minus 1 times minus 1, which gives 1. Okay, and go ahead and work out a couple more exponents and you'll see a repeating pattern. Okay? Now, it gets better. We can also think of imaginary numbers as points on a plane. Okay? Right now, I've shown you numbers multiplied by I. Now, in general, you will have what's called an old regular number, a real part, and then added to that, you can have what's called the imaginary part. This is the real part, and we call this one the imaginary part. Okay? Now, in general, when you have a number like this that has a real and imaginary part, or maybe it just has one or the other, but these type of numbers are called complex numbers. Not because they're somehow the most complex thing ever encountered in math, but I don't know why they're called that, but that's just what they are. Okay, complex numbers. Complex numbers, you could say, are composed of a real part and an imaginary part that includes I. Okay, now I want to end with the following observation. Notice that that looks a lot like the ordered pair 3, 2. Okay, we take advantage of that because we can do what's called plotting on the complex plane. Okay, it's not going to be x and y. Suppose that I took the real number line, which we already are familiar with. So 1, 2, 3, and then on the other side minus 1, minus 2, minus 3, etc., etc. That's the number line we've all got accustomed to. But now let me make a perpendicular number line, and this one I'm going to call the imaginary number line. Okay, and I'm still going to number that 1, 2, similarly, etc., etc., minus 1, minus 2. Okay, I can view 3 plus 2i. I can treat that as 3 comma 2, so you already know how to plot xy coordinates the old way, the familiar way. So can you see that this point, this black dot right where I've drawn it, can you see that that's a good way to represent the complex number 3 plus 2i? So that's 3 comma 2, and that corresponds to 3 plus 2i. Now, you can do this with any complex number. You can put this in what's called the complex plane. That's just a way to give a pictorial representation of all this complex number business. All right? Let me give you 2 other numbers to try. Try to show me where, actually I'm going to give you more than 2. How about minus 1 minus I, do that number, do 2 plus 3i, do the number 1, and do the number minus I. Okay, try to put, you maybe pause the video and try to put the dots in the complex plane for those 4 complex numbers. Okay, now notice that the last 2 complex numbers don't have 2 parts added together. Okay, if that bothers you, you can think of the third one as adding a 0i, so you have a 0 imaginary part. The minus I, you can think of that as 0 plus minus 1 times I, if you like. Okay, hopefully that doesn't surprise anybody. All right, so go ahead and plot those, try to plot those if you can. Okay, so this is, let me go ahead and show you what each of my dots that I drew corresponds to. So this one corresponds to 2 plus 3i. This one corresponds to 1. This one corresponds to minus I. And this one corresponds to minus 1 minus I.